All right, here we go. Lesson 1-4. This last unit of chapter 1 is about combinations, aka groups. So unlike the previous lesson in 1-3, where we were talking about arrangements, here our arrangements order will not matter. So whether you have, for example, A, B, C, or A, C, B, or any combinations of those three letters, they will all be the same. We'll only want one of them. Okay? So our numbers in answers in 1-4 will be smaller than our answers in 1-3 because there'll be less combinations because we're ignoring order. All right. So let's go through an example of how we might do this. Say we're designing cereal box ads. And in this ad, you have to have 2 of the 5 different stickers in each box. So how many different boxes of cereal are there on the shelves? For simplicity's sake, let's call our stickers A, B, C, D, and E. First of all, let's look at those that have sticker A. So that would be AB, AC, AD, and AE. Now when I come to sticker B, I'm not going to include BA because that one's already there. So I'll just have BC, BD, and BE. Notice there's one less than the previous one. And with sticker C, why, there'll be one less again because I don't want to include CB or CA. So it's just going to be CD and CE. Notice how I'm making an organized list. And my last one is going to be DE because again, I've already have the other 3. Notice I don't have to start with E because I already have them all listed out here. So if I add these up, 4 plus 3 plus 2 plus 1, I have 10 boxes. Notice, had we paid attention to order, in this case, and we had done the problem like we did last unit, I'd be doing 5p2, which would be 5 factorial, over 5 minus 3 is 2. 5 minus 2 is 3 factorial. So that would be 5 times 4, which is 20. Notice how that answer is twice this answer of 10. Yeah? It's not always going to be twice, but notice it's greater. And so this takes us now to our next example. And this one hopefully will drive us to looking for an answer. A shortcut. 30 students are in a class, and they're told to create pairs between themselves. How many different pairs are possible? So if you look at just the first student, he has 20 options. Sorry, he has 29 students they could pair up with. And the next student, because they've already been paired with the first student, and they're not going to pair with themselves, obviously, so then that would be 28 options. And the third student would then have one less because they've already been paired with the others. So this would be a rather long list of things that we would have to add up. 29 plus 28 plus 27, right, all the way on down. And clearly there must be a shortcut. Well, there is. If I think about this as every student has 29 options, yeah? So the 30 students each has 29 options. Then I've actually ended up double counting this number. Meaning, notice if I had not had 28 here, or in 27 here, but I had 29 every time, I would end up having twice as many as I did because I would be double counting every pair. Does that make sense? So if we take this answer and divide by 2, yeah, kind of like we noticed that shortcut up here was 5 times 4, divide by 2. This does end up giving me the correct answer. which is 15 times 29, which I'm now trying to do on my calculator. 15 times 29. I get 435. Okay. I'm now going to use our formula, or combinations formula, to get that same answer using this. And this is the formula that we're going to use. We've got to be careful here. Note that we're not always going to be dividing by 2. We're going to divide by other numbers if there's, like, not pairs, but for example, if I have a group of 3 or a group of 4, right? How do I, like, reduce those duplicates? So let's use this formula right here that's in the box. And let me show you how it works. N is the number of total items, and R is the number of items in each group. So in the last problem, we had 30 kids. I was choosing groups of 2. So the formula says take 30 factorial divided by, notice it still says n minus r, so 30 minus 2, I get 28 factorial. Hopefully I didn't do that too fast. And then there's one other thing, and this is the additional thing I need to divide by, and that's going to be by whatever number is there, take a factorial of it. So one of the things I tell kids that if you want to know if you're doing this right, notice the denominator has 28 and 2, and that's not a coincidence that it kind of adds up to 30, excuse me. All right. So again, this is 30 times 29 times 28, blah, 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 all the way down, right? And on the bottom I have 28 times 27 times 26 times blah, 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 times 1, and then I have the other piece, which is 2 times 1. So the 28, all that cancels with this all the way down to 1, yeah? So I'm going to have 30 times 29 divided by 2. And yes, that gives me the same answer as 435. All right, so this formula does work. It's called a combinations formula, and it should be in your notes. Take a moment, pause the video, copy it down. We're now going to use it in a couple of our last example. So we've got a marathon here of 50 runners. The top 10 advance to the Olympic qualifiers. Also, the top 3 get cash prizes, which are each different, depending on if you place first, second, or third. So we've got 2 different problems going on. Number 1, how many ways are there to advance to the Olympic qualifiers? And then how many ways are there to win a cash prize? All right, well, let's do both of them separately. This first one, clearly order does not matter. But this second one, order does matter, meaning if you get first or second or third place. In the first one, all we have to do is be in the top 10. So in the first problem, we're doing a combination of 50 things, and I'm picking 10 of them. Whereas in the last one, I am doing a picking from 50 things. I am choosing 3 of them. All right, and so here we go, 50 factorial. Notice how they both start the same way, yeah? And then in your denominator, now you got to subtract 50 minus 10, subtract those 2, so you get 40. And then recall that in combinations you need the extra piece, and that's just this one. So 10 factorial. And we'll go to our calculator and punch that in. Whereas in this last one here, where we're doing how many ways, we just have to subtract that and get 47. So this one here, we know it's going to be 50 times 49 times 48. Remember, that was kind of like the fundamental counting principle, that we have 50 ways to choose first place, second place, and third place. So this bottom answer, I'm going to use Desmos in each of these, and I've got it up and running. So again, I'm going to type in functions and stats, and let me make this a little bit larger. There we go. So n CR, and 50, comma, 10. All right, and that's giving me a number now in scientific notation, 1.027. I'm going to round it off at that point and then say times 10 to the 10th. So 1.027 times 10 to the 10th. What is that number? Well, let's slide the decimal spot 10 places. So there's 3, and I've got to go 7 more zeros after that. Okay? So 1, 2, 3, 4, 5, 6, 7. So that's like 10 billion ways for these 10 runners to qualify. All right? And now I'm going to do the last one. And enter. And now again, I'll go back to functions, and I'm going to choose NPR, N50, choose 3. And that's 117,600. Now, you may say to yourself, Mr. Larson, I thought you said that combinations is less. And that's true. But in this case, notice, in the first example, we were choosing 10 things, groups of 10. Whereas here we're only choosing groups of 3. And here the order mattered. So if I had these numbers the same, then yes, permutations will always be smaller than combinations. But hopefully you are able to understand how to use that formula again. There's now just 2 things in my denominator I've got to be careful of. And always pay attention to order. If order matters, use the combinations. Use permutations. If order doesn't matter, then use combinations. Okay. Hopefully the problems go well for you.